Hello, once again. I hope you're having an amazing time at PyCascades 2022. We have our second talk of the day by Pradhvan Bisht, and the topic of the talk is Python's tale of concurrency. Python is underrated when it comes to concurrency. The main aim of the talk would focus on exploring the general concept of concurrency and how we can utilize these concepts to write Python programs that are more scalable and more efficient in terms of input-output bound operations. Before we move to our talk, I just want to take a moment and talk about our presenter. Pradhvan is the Pythonista that loves playing around with web technologies and an interest in backend development. Strongly believes in the free open source software ideology, thus tries to give to the FOSS communities however he can. Pradhvan, stage is yours.
Hello everyone, welcome to my talk, Python's Tale of Concurrency. This is a general introduction to concurrency through the lens of a Pythonista. If you are someone new to the concept of concurrency, you are the perfect audience for the talk. I hope this talk excites you to explore the paradigm of asynchronous programming and gives you a solid ground to tinker on your own. Just a brief introduction, I'm Pradhvan. I love all things open source. I'm a backend developer by profession. Let's start this talk by understanding what concurrency actually is and why anyone should explore this paradigm of programming. Let's build a hypothetical service around coffee and call it coffee as a service. So how this service works is the user comes in, requests the order, waits until the order is prepared, and once the order is completed, the second user gets the access of the service. So the whole flow is order, wait, move, and continue. Now with passing time, a service gets lucky and we get a decent traction. But you notice a few complaints often. The complaint that the service becomes a bit slow when you get a lot of users, which is true. A service is as fast as a slow order in the queue, and when we get a lot of users, the chance of slow order also increases. Realizing this, you set out on a goal to fix this problem, and this is where the concept of concurrency comes into picture. Wikipedia defines it as concurrency is the ability of different parts of a program to be executed out of order or in partial order when affecting the final outcome. Or as Rob Pike puts it, concurrency is about dealing with a lot of things at once. If you look into a real world example, one good example that I could think of is of a hurdle race where an athlete runs and jumps, not doing both at the same time. Coming back to our service, now that we have a brief idea of what concurrency is, let's see how we can decrease the wait time. Doing some minor adjustment, what we can do is we can add a barista. A barista can take future orders, even do preps for them while the first order is being made, which would eventually decrease our waiting time. Right? And if I talk more in terms of programming, we can say that barista in this session acted as a scheduler for our service, but more on that later. Another obvious way to solve this problem could have been just add more machines. That way, we could have easily processed one or more headers at a time. This solution is also correct, and in programming terms, we would call it parallelism. That's a different tale for a different talk. In this talk, what we can see is how concurrency is different from parallelism, so we don't confuse it often. Concurrency is a slightly broader term than parallelism. In concurrency, multiple tasks have the ability to run in an overlapping manner, whereas parallelism, they are executed at the same instance. One is structure, the other is about execution. Now that we have a basic straight, let's see how Python handles concurrency. Two major and widely used ways in which Python handles concurrency is by utilizing the threading library to create threads or taking advantage of async IO. Moving forward in this talk, let's take a very trivial problem that fetches certain comics and try to solve it in two ways. The first solution could be a sequential and a very straightforward one. The second solution would involve us to use concurrency. That way, on comparison, we can see that how concurrency is different than sequential programming, what concurrency actually is, and the most important, how Python handles concurrency. So let's start off with the first solution. We create a function called getComic. Let's see this as a base function. The only task for this function is to make a request to a particular comic number URL and fetch its data, and finally add that data to the list. Pretty straightforward. The comic that we need to fetch are stored in the list called comic numbers, and we are making it a list just for the simplicity's sake. To get the respective data, we can just iterate over the list and fetch out, and using a getComic method, fetch those comics. Well, that's it. That's sufficient. It's simple, gets stuff done, and is sequential. That is, for every request that we send to the server to get the comic data, the request waits for its turn to be completed and then moves on to the next. And if we time our program, we can see that it only took 1.84 seconds. Well, it's good. Before moving forward to our solution with threads, let's first understand what threads actually are. Python threads are implemented using operating system threads. The interpreter runs on the main thread and on demand can execute a separate flow of threads. IO bound tasks are the best use case of threads because Python has something called as a global interpreter lock, or the GIL as most people call it, which only lets one thread to run at a time. Let's look into a very simplistic execution diagram to see how two threads run. Here you can see that when thread 1 runs, it acquires the GIL, and in the meantime thread 2 waits, and thread 2 is only executed when the thread 1 gives the block or the GIL, and then only thread 2 can execute it. Going in a similar manner, thread 2 executes when it gets GIL, and in the meantime thread 1 waits. This is very simple. But what if there are 3 or 4 threads? It gets complicated very quick, isn't it? Moving back to our problem with threads, GIL doesn't bother us much here because most of the tasks that we're doing here is around output or IO as we call it. So we can make our threads to wait while it's sending a second request. So keeping the base function, the getComic method, the same, what we did extra here was just to import the threading library. Since we have a limited number of comics to fetch, let's spawn a thread for each of them and see how it goes. Created an empty threads list which would store thread instance. So like last time, iterating over all comics, create a thread instance. The target method gets the getComic method or a base function to fetch the data. The arguments is the comic number, and we append that thread instance to the threads list and finally start that thread. Let's see what would happen when we run this program. You notice one thing here. Since we ran the program multiple times, the ordering in which it's fetching or the thing it's fetching changes. Well, this is because The context switching in threads happen through operating system, and as a user, very little say in it. So when we start a thread, it is eventually being started, but we need to do one more thing. So we can get the data out of it. We need to join the threads. Calling a join on the instance waits until the threads is terminated. This blocks calling other thread instances join while this method is terminated. If we only call the start method, what would happen is the threads would eventually start and eventually die, giving us only two things. If the target functions run successfully, it would do nothing, and if it creates an execution, then also it would do nothing, because we haven't called a join on it. Join also accepts a floating point integer, which you can decide on how long you want to block the thread, ignoring the threads that aren't ready. Here in line 5, you can see that we have added a 0.2, because that way we are asking the thread to wait 0.2 seconds. Though if you decide to set out a timeout value, you would need to check that if the thread is alive or not. If the thread is still alive after a join, it basically means the join failed. You can notice on line number 6, we have added a not condition. Hence, threads is successfully joined, we just remove it from the threads list. And if you don't want to get into the whole hassle of starting and joining a thread, you can also use something called as a thread pool executor. A thread pool executor uses threads to execute calls asynchronously, and if you use it with a context manager, like here we have done, when it can automatically call the join. That way you will get the data. Finally, if we run this program and compare it with asynchronous version, we can see that the threading program is much faster. Another way you can write concurrent code with Python is through asyncio. Asyncio utilizes the power of an event loop that executes function which can be suspended when they need to wait and restart it when the wait is over. Asyncio is mostly single-threaded and utilizes the single-threaded completely. Here, the user has the control of the context switching. Thus, we call it cooperative multitasking. Since async tackles the problem of concurrency in a different manner than thread, it also introduces some new concepts. The most common ones are asynchronous functions or async functions. These are different than your normal functions and don't block, and non-blocking. Coroutines, event loop, the brain mind suspending and restarting tasks, and eventually tasks. Let's understand each one of them one by one. Asynchronous or async functions. Normal functions, as I told you, blocking in nature. What I mean by that is they stop the flow of execution until they return something. Since in a typical asyncio based program, everything runs under a single thread and all functions are executed by a single loop. Thus, to be concurrent, those functions to be non-blocking in nature, and to make it possible, new async keyword was introduced so that we can keep those async functions. Await, on the other hand, blocks the execution until what is awaited is finished. Though when we await, other things can in the background. Thus, the context switching control is passed on to the user, which leads to cooperative multitasking and things can run concurrently. In the given screenshot, what you can see is I've also used asyncio.sleep to wait for at least 1 second instead of time.sleep. There is a reason for that. This is because time.sleep is a blocking call and asyncio.sleep isn't. With time.sleep, you don't return control to the event loop. You hold up everything and nothing else happens. On the other hand, asyncio doesn't block the entire execution of the program. Seeing this, you must have realized now. If you are writing a concurrent program with asyncio, you might have to ditch some of your standard functions and libraries so that you get the most of it. Coroutines, on the other, are awaitable objects that are created with asynchronous functions. Here you can see on line 8, coro is a coroutine which further is made clear when we call a type method on. Coroutines do 3 things commonly: wait for a forthcoming result, awaits another coroutine, or return the result. Most folks commonly interchange async functions and coroutine. But Lucas Langer gave this neat little distinction between async functions and coroutines, which I find very useful. Async functions is the definition and is used to create coroutine when called. Coroutines in turn are awaitables and you can create them by calling async function. So what I mean by is, coroutines are awaitables but async functions are not. Moving on to the event loop. The heart of every async program is the event loop. The only job of it is to schedule callbacks and not actively wait, so we can concurrently run our program. Python also allows us to directly use the loop object, like here you can see in line 2, done through asyncio.getLoop. And if we print that loop, we can see there are some common information regarding it, like what protocol it uses, its debug, and it's running or not. The ability to use the loop object directly gives us a very good freedom to use libraries that only support asyncio or uses event loop in some way or the other. One such project that I could think of is Puppeteer. Puppeteer is a library that forces you to use asyncio, but if your code base doesn't require you an event loop or is not written or is written in a traditional manner, you can use that loop object and call that loop object using Puppeteer and have a separate instance. Though most of the time you would be dealing with a high function that was introduced by asyncio called asyncio.run. Asyncio.run provides an elegant way to do three things: getting the event loop, running tasks until they are completed, and then finally closing the event loop. One really interesting thing that Python gives you is the ability to use a different event loop if you are running on, let's say, production. This is UV loop. UV loop uses Python, so it's completely fast. So using UV loop and asyncio combined, you can write very high performing netting code. Now that we know enough about asyncio, let's use our knowledge to write the same function of extracting comics with asyncio. Besides importing asyncio, I've also replaced request with HTTPX. HTTPX is an HTTP client library, Python, which has its async client, which we'll be using. And besides the base method, I've only converted this base method to with an async definition to make it an async function. Converting a main function, we can see that we are still following the same approach, iterating over the numbers and just awaiting on the coroutine. And if we run this, we could see something strange. Even though it ran with asyncio, it's comparatively not that fast and it's still behaving like a synchronous function. This is because await blocks the execution. Remember, this is a common pitfall that most of the people make when starting out with asyncio, and it brings us to the next topic called tasks. Tasks are used to schedule coroutines. When you wrap a coroutine with a task, it independently schedules for execution by the event. Just like a previous example, even though we were running it with asyncio, we still forgot one major thing: await blocks the execution, right? So if we want to await on multiple coroutines, it's to use the gather method so that tasks can be waited concurrently. Now that we know how we can fix our problem, let's see the updated code. Now, instead of awaiting on every response of getComic, what we are doing is we are creating a list of tasks and iterating over the next numbers. We are creating a task with asyncio.createTask, and like last time, passing a client, which is an HTTPX client, and the comic number. Finally, since we have created multiple tasks and scheduled them to run independently, we can await them only once using the gather method. Let's run this and see the results. Much faster, right? Asyncio is definitely a robust solution and makes writing concurrent programs that are IO heavy, but it is easy to fall into a false sense of security and underestimate the complexity of concurrencies that it brings us. It's not always wise to make asyncio your default solution and use it as a silver bullet. If you think threads can do the job, definitely go for them. Remember, concurrency is still hard to deal with. With this introductory talk on concurrency and the time limit I had, I could only scratch the surface of what there is to concurrency. There is a lot more in store when you actually tackle real problems and problems with concurrency, and sometimes concurrency adds those extra layers, already difficult parts of a program which you can or you can't find using debugging, or add more problem to testing and profiling. So before ending this talk, I'm going to leave you with some resources from folks who have a lot of hands-on experience with asyncio. First one is from Lucas Langer. Lucas has created a video series on asyncio. Six episodes out of which are already out. So feel free to check them out on HDB's YouTube channel. Second one is from Lynn. It's a blog post series which tackles real world problem with asyncio. Lynn also has a complementing talk with it. One thing to note here is the resources are comprehensive. So I would suggest to work with them in your own time. That I have for you today. I have this talk gave you a solid ground to tackle concurrency and sets you up good when you are trying it out on your own. Before ending this, I'd like to thank Lucas for his videos and the efforts towards Python's asynchronous stack, to Lynn for the very well crafted and insightful tutorial on asyncio, and the effort Lynn has put in in increasing the diversity in the community through PyLadies. To all the members of PyCascades, all the volunteers, speakers, and attendees, and finally to Lacey Williams. Her talk in PyCascades inspired me to add this slide where she was acknowledging everyone. Because her talk was on Django REST framework, and she was acknowledging everyone that had worked towards Django REST framework and building it to whatever it is. And thank you for attending my talk. I hope this brought more clarity and you explored the paradigm of concurrent programming.
Mohammed, you're muted.
Thank you, Pradhvan, for your talk and taking time to teach us about this topic, concurrency in Python. We are noticing an issue with captions in Firefox. Please try searching through Chrome, should resolve them. We do have a Q&A session with Pradhvan. Make sure to join Q&A room within Venuless. It should be on the left side under navigation. Now we have lunch time from 11:40 a.m. PST to 12:45 PST. So make sure you fill yourself up with delicious food so you can have energy to enjoy your rest of the amazing talks happening today. After lunch, we will have a talk on building elegant API contracts from zero to hero by Neeraj Pandey. Also, don't forget to check out boots by Microsoft and PyLadies. Each have a virtual boot right here in Venuless. Lastly, don't forget to share us on social media and tag us on Twitter. Our Twitter handle is @PyCascades, all lowercase, and definitely check out our photo booth on photobooth.pycascades.com.